Hello everyone, welcome back. For today, we will now have a discussion on energy balances using heat effects. Now, in order to have a better understanding on heat effect calculations, you have to define what we call a process path. Now, recall that enthalpy is a state function. Thus, changes in enthalpy is only dictated by the initial and final states and not the calculation path that the process will take. So if the calculation path is composed of multiple steps, we can combine these multiple steps to form the overall calculation of our process. So for example, we have a process starting from state 1, from temperature T1, P1, and let's say liquid. So this is the phase to state 2 at a certain temp T2, P2, and maybe vapor, and maybe a reaction occurred along the way. We have multiple steps occurring in this process. And the process path can now be composed of multiple individual calculations. So the usual process paths that we take are a change in pressure, holding temperature, and phase constant. We also have a change in temperature, holding pressure or volume, and phase constant. And this is known as your sensible heat. You also have a change in phase at constant temperature and pressure. And this is known as your latent heat. You also have a change in composition for a chemical reaction at constant pressure, temperature, and maybe phase, or possibly hindi rin pala. Okay, kasi that can also be incorporated in the change in composition, the enthalpy. So these are your heats of reaction. And last, you have your mixing and dissolution heats at constant temperature and pressure. And this will be more covered in ChemE 123. So to start, the change in pressure at constant temperature and phase, there are two cases. The first case is for condensed phases, solids and liquids. And for these types of matter, the change in volume with respect to pressure is not appreciable. Thus, delta V is approximately equal to 0. Now, as for the change in internal energy, recall that internal energy is mostly just a function of temperature and a very, very weak function of pressure. Thus, delta U is approximately equal to 0. Now, what about enthalpy? Okay, for enthalpy, recall H is equal to U plus PV. Thus, delta H is equal to delta U plus delta PV. Okay, if delta V is approximately equal to 0, so therefore delta H is equal to V times delta P. So delta H is approximately equal to V delta P, where V is a specific or molar volume at this particular temperature. And for ideal gases, delta U is equal to 0, and delta H is also approximately equal to 0, since U and H for ideal gases are independent of pressure. Okay, next up is sensible heat. And sensible heat is heat transferred to a system in which there are no phase transition, no chemical reactions, and no changes in composition. So it's purely temperature change only. And for an ideal gas, delta H is simply equal to the integral of Cp dt. Now, if Cp is constant, delta H is just equal to Cp delta T. However, if you recall from your Chem E102, that Cp may also be a function of temperature as such. So Cpig over R can be a linear polynomial function, as this one, which is tabulated in SVA. And also, you can refer to SVA Appendix C, so Appendix B at that, Table C in that point 1, for the heat capacities of gases in the ideal gas state. Okay. Pero if we take a look at this, for example, sa air, okay, take a look at Cpig over R of air, it's 3.5, which is approximately 7 halves. So ginagamit natin dati na 7 halves R, na Cp of air, is almost valid, okay, for a particular condition. However, in most cases, it's actually still a function of temperature. So now, how do you evaluate delta H, or the sensible heat, for a gas mixture? So there are three options. One is to calculate the individual delta H for each species. So let's say you have multiple species, for example, air. So kunwari air, kunin natin 79% N2, 21% O2. So to get delta H of air. So delta H of O2 plus delta H of N2. Pero delta H of O2 multiplied by number of moles of O2, and syempre with N2 multiplied by the number of moles of N2 as well. Another option here is to use the molal average heat capacity, where A prime is summation of Yi Ai, and so on. So with this, delta H is equal to N equals CPIG mixture T1 from T1 to T2 dt. Okay, where A prime is, for example here, A prime is equal to 0.21 A of O2 plus 0.79 A of N2. Tapos multiply by the number of moles of the gas mixture. And last but not least, you can also factor in the total moles inside the integral instead of calculating the molar average heat capacity. So this is more useful kapag ang given mo ay naka-molar flow rate or naka-total moles. Tapos yung second one is more useful kapag composition ang binigay sa inyo or kung meron kang given. So with this, just to factor in, so delta H is equal to R integral of T1 to T2. Parang same lang pero naka-summation na yung NA. So for example, you have 100 moles of air. So summation of Na is equal to 21 times AO2 plus 79A N2. Okay, so to illustrate this, let's have a brief example. So you have a mixture of 1:3 N2 to H2 flowing at a rate of 200 moles per minute, which is to be preheated from 300 Kelvin to 800 Kelvin in a heat exchanger before feeding to the ammonia reactor. Calculate the required heat transfer rate in kilowatts for this process. Let's use the three options using the assumption that the heat capacity of the two species are functions of temperature. So option 1, let's calculate the sensible heat change of each species individually. So first, delta H of N2. Okay, so ito yung moles of N2. Conversion factor lang from minutes to 60 seconds. Tapos, let's use the ideal gas constant na 8.314 raised to negative times 10 to raised to negative 3 kilojoules per mole K para medyo maganda yung units. Naka-kilowatts tayo. And nasa loob ng integral ngayon, yung respective values ng heat capacity constants natin. And evaluate the integral. Yan. And you can also do the same for H2. Ayan. So calculating, delta H of N2 is 12.55 kilowatts, and delta H of H2 is 36.54 kilowatts. And the total delta H of the process is the addition lang, which is 49.09 kilowatts. Now, your second option is to calculate the molar average properties of the coefficients of the ideal gas relationship between temperature and heat capacity. So in this, let's calculate A prime. So A prime is the first for N2, okay, 1/4 ang composition ng N2, and 3/4 ang composition ng H2. So you can get A prime, which is the molar average A prime, or A coefficient. And you can do the same for B and for D as well. Using this, delta H total is equal to, ito na yung total, N dot. So again, same R. Tapos, ito yung CPIG ng mixture natin. And evaluating the integral, you should still get 49.09 kilowatts. Okay, now, last but definitely not the least, is to factor in the total moles into the integral. So, calculate natin summation of Na, Nd, and so on. So, the summation of Na is equal to the moles of N2, here, which is 50. Nakamultiply na siya. 200 times 1/4. So, ito yung moles of N2 times A of N2 plus moles of H2 times A of H2, which will give us summation of Na here. And you can do the same for B and for D. And now, delta H total is equal to, again, conversion factor lang muna for minutes to seconds para kilowatts lahat. And ito yung CPIG and CPIG mixture. Thus, delta H total is 49.09 kilowatts still. So the three methods Up to you, whichever one you want to use depending on the situation. Pero I prefer mix option 3 kapag mas madami, pag yung given natin is naka-molar flow rate or total moles, I usually prefer option 2 kapag naka-composition yung given. Option 1, kayo na bahala kung gusto yung gamitin yun. Pero typically ginagamit ko pag siguro 2 lang, sige, dalawa lang. Pero pag more than 2, di na pick between option 2 and 3 sana. Okay, now sometimes, mas maganda gamitin, instead of the integral form, we can make use of the integrated form of the sensible heat expression. So to do this, let's just simply integrate this working expression. Integrate natin from T0 to T1. So delta H is equal to R. Tapos ito yung expression natin. And then, recall, this is a sum of difference of two squares, difference of two cubes. Recall your pre-calculus. And you can replace these with the following. Ayan, so ito, in-expand natin. And pansin nyo, you can now factor out T minus T0. Factoring out T minus T0, you can get delta H is equal to R times this whole expression times T minus T0. And the maganda sa form na to, as you can see, you will get a form such that delta H is equal to Cp times dT, or delta T, where Cp mean here is the average heat capacity of the gas between the two temperatures T0 and T. And this is useful for iterative calculations. Okay, let's have an example for an iterative calculation. So calculate the final temperature when heat in the amount of 422 megajoules per hour is added to ammonia initially at 260 degrees Celsius or 533.15 Kelvin, flowing at a rate of 11.3 kilomoles per hour. Okay. Given the following ideal gas coefficients for heat capacity dependence on temperature, so delta H is equal to Cp mean times T minus T0, which is equal to Q, and this is our energy balance equation, again assuming negligible kinetic potential energy changes and there is no shaft work. Thus, for total heat rate, N dot times Cp mean T minus T naught is equal to Q dot. So multiply natin by N dot to get naka-flow rate na tayo. Okay? So N dot natin dito is 11.3 kilomoles per hour. Tapos Q is 422 megajoules per hour. Now, to start this, expand natin si Cp mean. Okay? Recall, from our integrated heat capacity equation, Cp mean is this whole expression. So yan yung Cp mean. N dot R times this expression, T minus T naught is equal to Q. And to start iteration, gagawin natin is we will make use of what we call fixed point iteration. So we will isolate T as a function of T. Okay, so kuha tayo ng expression and usually ginagamit natin for iterative calculations. Ito. So isolate for this T. So just move everything here to the right-hand side. Tapos, galawin din natin dyan. So T minus T naught is equal to this expression. Thus, T is equal to T naught plus this whole expression. So, paano to? So, ito yung steps. So, usually, we will guess an initial value of the temperature and then calculate the right-hand side and then get a new value of temperature and then repeat step 2 to 3 until convergence. Okay, so to illustrate this, ito na yung working expression natin kanina. Naka-substitute na dito yung necessary values. Take note lang na kinonvert ko lang itong Q into kilojoules per hour para consistent yung mga units natin. Okay, so lahat ng energy, make sure na naka-consistent yung units. Ito, kilojoules, N natin, kilomoles. Okay, gas constant natin, kilojoules per kilomole. So temperature natin dito lagi is dapat naka-Kelvin pag i-evaluate yung integral. So setting initial guess of 1000 Kelvin, plug it here into the right-hand side. So hindi to shift solve plug in dito sa temperature na yan and sa temperature na to yung 1000 Kelvin. And kapag na-plug in yun na, you will get a new value of the left-hand side. So itong value na to, makuha nyo 1299.93. Okay, so now, makuha natin dito ngayon, yung new temperature natin is not equal to our gas temperature. So what we will do now is we will circle back. We will now use this new value of the temperature and substitute this back into the right-hand side of the expression. So, ulitin nyo yan until you reach a certain convergence. So, nag-substitute tayo. Ito yung makuha natin, 1, 2, 4, 3 sa pangalawang iteration and hindi pa rin siya equal. So, repeat this until a certain tolerance is met. So, for this problem's sake, let's just use an absolute difference of 0.1 Kelvin or less. You can be more stringent or be more relaxed, pero ito, sige, pwede na. Okay, so typically, pwede natin gawin 0.1% na relative difference, pero ngayon, absolute difference lang muna. And for this certain convergence tolerance, you will get the final temperature, which is 1252.29 Kelvin. And if you want to take a look at the summary of the iterations, so using an initial guess of 1000 Kelvin, ito yung first iteration, second, third, fourth, fifth, and sixth iteration. At the sixth iteration, medyo pasok na siya sa convergence tolerance natin. Okay, so at least itong method na to, sure tayo na magkakaroon ng quick convergence. Okay, so that's it for the sensible heat change. Let's now proceed to the next one, which is your latent heat change. Now, for latent heat, this is defined as a specific enthalpy change associated with the transition of phase of the substance, okay, at constant temperature and pressure. And typically, these phase changes are accompanied by large amounts of internal energy and enthalpy changes. So typical latent heats that we have, the latent heat of fusion and the latent heat of vaporization. So latent heat of fusion is given by enthalpy of the liquid minus enthalpy of the solid. And the latent heat of vaporization is given by the heat of the vapor minus the enthalpy of the liquid. Okay, now, from your latent heat, okay, either heat release siya or heat absorbed during your phase change. Now, typically, for phase change processes, these will always occur at constant temperature and pressure. So recall your Gibbs degree of freedom analysis. So F is equal to 2 minus pi plus n. You have two phases and you have just one component. Thus, your degree of freedom is 1. So ngayon, if we know the temperature, you can also know the latent heat. So if you know the temperature, you can get either delta H vap or delta H of fusion. Or if you have the delta H of vaporization, this will correspond to a certain temperature for that heat of vaporization. Okay? So typically, the heats of fusion and vaporization are tabulated, pero nakatabulate dyan normally are the normal heats of fusion and vaporization. So pag normal, at the normal melting point or the normal boiling point, respectively. So now, how are other ways that we can calculate the heats of fusion or vaporization? At least for ChemE 122, mas mag-focus tayo sa heats of vaporization since we will be dealing with fluid systems. Heats of fusion, not so much. So purely liquid to vapor transitions or vapor to liquid transitions. So one of these equations, you can use the Clapeyron equation to estimate the latent heat of vaporization. However, there are also other ways to estimate this. First one is you have Troughton's rule. And for Troughton's rule, you can estimate the normal heat of vaporization at the normal boiling point is approximately equal to 10. So the ratio of delta H over RTN is approximately equal to 10. So this is not that accurate, pero good enough approximation daw according to Troughton. However, we also have other empirical relationships. So one is developed by Rydell. So the Rydell equation gives us a normal heat of vaporization given the normal boiling point and critical properties of the fluid. So we have PC, the critical pressure, and we have TRN, which is the reduced critical temperature. Reduced temperature. So usually TR is given by T over TC, but TRN, so the normal boiling point siya. So TN over TC. Okay. And here, PC should be in bar since Rydell developed this equation to use for naka-bar yung PC. Okay, so ginagamit again si Rydell to get normal heat of vaporization. Okay. Now, what about temperatures other than normal boiling point? So for that, we have Watson equation. And Watson equation gives us the ratios of two heats of vaporization as a function of the reduced temperature. Okay, so where Tr is equal to Tc again. So using the Watson equation, if we know one delta H of vaporization at a particular temperature, you can now estimate all other heats of vaporizations for all other temperatures. Okay, so to illustrate this, let's calculate the latent heat of vaporization of water at 100 degrees Celsius. So we know that 100 degrees Celsius is the normal boiling point of water. Yes, so using the Rydell correlation, delta Hn over Rtn is equal to this equation. So we now need to get the values of the critical pressure and the critical temperature and the normal boiling point. Okay, so kunin natin yan from SVA Appendix B. Nakatabulate yon. So SVA Appendix B. So with this, plug and play. This is the critical pressure and this is the critical temperature. And substituting, you can now get the normal heat of vaporization at 100 degrees Celsius, which is 42.039 kilojoules per mole. Now, comparing this to the steam table value, okay, so to convert into kilojoules per kilogram. So delta Hn using the Rydell correlation is 2335.47 kilojoules per kilogram. And delta Hn from steam table value is 2257 kilojoules per kilogram. So there is a slight discrepancy between the two, and this is expected since the Rydell correlation assumes somewhat ideal gas. Pero steam table does not assume ideal gas. So if you want a more accurate value for water, use the steam table. Madali lang gamitin yun. Pero pag hindi na water, baka limited na yung data natin and we have to resort to using this Rydell correlation in order to obtain the normal heat of vaporization for a particular substance. Okay, next naman, what if we want to estimate the latent heat of vaporization of water now at 300 degrees Celsius? So in order to do this, we can make use of the Watson correlation. So we have previously obtained the normal heat of vaporization using Watson. Assume wala muna tayong steam table. So we have obtained delta Hn using Rydell, sorry. And using Watson equation, okay, so alam na natin yung critical temperature. So we can set either one of these to be state 1. So gamitan natin, delta H1 is delta H and TR1, this is now TRN since ano yung given na value natin. So using this, substituting our known values, you can now get the heat of vaporization at 300 degrees Celsius, which is 25.56 kilojoules per mole. Converting this to kilojoules per kilogram, it's 1420. And comparing this to the steam table value, which is 1406 kilojoules per kilogram. So as you can see from here, the latent heat of vaporization at higher temperatures are much less compared to lower temperatures. Kanina, 42.039, ngayon, 25.56. This is expected since the higher the temperature, the less the difference between the enthalpies of your vapor and your liquid state. Alright, so that ends the first part of our discussion on heat effects. So far, discussed natin 3, change in pressure, change in temperature, and change in phase. And these are your non-reactive heat effects. The next part naman will involve heats of reaction and energy balances involving chemical reactions.